Institute is the world's leading venue for collaborative research in theoretical computer science. And it was established in 2012 by a grant from the Simons Foundation, who continues to support us. And broadly, the goal of the Institute's semester programs, clusters, workshops, other outreach activities is to explore the use of algorithmic thinking in computer science and adjacent fields, and to have focused efforts to understand the laws of computation itself. So a few logistics before we start with the workshop. So food is provided outside in the breaks. Food and coffee is provided. Lunch is not provided. And you're welcome to go check out the restaurants nearby for lunch. One useful thing you can do, there are some lockers on that side of the building where you can leave your stuff when you go out to lunch. And we do ask that you don't bring food back here in to keep the auditorium clean. So that's all about food. The other thing is all the talks are recorded and by our videographer, Omid Farr, who's over there. So if anyone has any problems, then he'll help you during the talk or during the workshop. Finally, we do invite you to, if you're going to tweet about this, we invite you to do so, but do tag us on Twitter at Simons Institute, and we will retweet you. And finally, I want to give a big thanks to Ashley Hassan, who did all of the logistics for this workshop, including reimbursements, accommodation, etc. So thank you, and here's Jelani, who will say some more things.
Hey, morning, everyone. Maybe just before we start with the first talk by Mert, let me just say a couple things about the schedule. So we do have an open problem session tomorrow. That's 4 to 5 p.m. You're not required to tell us your open problems ahead of time, but if you want to, there's always like this awkward thing I've sometimes seen at the beginning where we say, okay, now the open problem session, and then there's a pause at the beginning where we have to push people to start. So if you want to help us get started off immediately, just email me and say, I want to present an open problem. And if you want to say your problem in the email, you can. I'll just write down my email here. Okay, so that's for the open problem session tomorrow, 4 to 5 p.m. We'll also have lightning talks tomorrow morning. And that's just a way for people to introduce themselves and what they work on to the rest of you. If you want to give a lightning talk, 3 minutes max, okay, or shorter, also just send an email. And probably also send me a PDF of your slides so that we can transition more quickly. Other than that, there are some discussion slots that are built into the schedule at the end of some days. Those are more just like breaks where we encourage you to stick around and talk to each other. It's nothing formal. Okay, so with that being said, oh, and there was a question about ventilation and air conditioning. Okay, so we don't have air conditioning in this building, unfortunately. I asked. Most buildings don't in the East Bay, but the best we have are fans, and we put the fans on max, but we'll see how well that works out. Okay, so, last thing, very last thing, I promise. During Q&As, please ask your questions into a mic. We have 2 mics. We'll pass mics around. And we also ask the speaker answer questions into the mic because this is being recorded and put on YouTube. So for the benefit of those who are not in the room, we would like everything to be recorded. It'd also be helpful for speakers if you could repeat questions that are asked to you. Okay, thank you. So let's begin.
Okay, first of all, I'd like to thank the organizers for the kind invitation, and thank you, all of you, for being here. So I'll be talking about randomized embeddings and neural networks. So I'll start with some current challenges we're facing with deep neural networks. Then I'll introduce you what a randomized embeddings is. It's a mathematical construction that we use in sketching methods to make higher dimensional data lower dimensional. Then I'll introduce you a model for neural networks based on convex optimization. So this part will be new. And we will use randomized embeddings in these convex programs for solving neural network problems. And finally, I will show you a unifying framework based on Clifford algebra, if you have enough time. So we have witnessed the impact of deep neural networks. They are working extremely efficiently in computer vision, robotics, more recently in language models. I'm sure you heard of ChatGPT. I asked ChatGPT, what does a sketch mean in the context of randomized algorithms? And it gives you a very good answer. In the context of randomized algorithms, the sketch is a compressed representation of data The goal is to capture the essential features of a data set. And the purpose of this is to allow algorithms work on massive data sets. And we usually have randomized constructions based on random matrices or some hashing function. Actually, today now you can also ask ChatGPT to generate an image, a description, an illustration. This is the DALL-E model. It comes up with this. It's a funnel metaphor. So massive data goes in, and then you have sketch coming out. This is done by randomized algorithms. The sketch extracts this essential part of the data set. This is done with a neural network tool. It is a diffusion model. These diffusion models, they basically create hallucinations from random noise. They work amazingly well. But sometimes you don't want hallucinations. This is one example. In medical imaging, neural networks, similar to the ones in the diffusion model, are used to denoise and magnetic resonance imaging signal. And it turns out, actually, in the reconstruction, it hallucinates a false vessel. This is not really there. It is imagined by the neural network. So this is, of course, not acceptable for medical imaging. So the point I'm trying to make is deep learning is really working great, but they are complex black box systems. It is based on massive amounts of data. These models are also extremely large. Models like GPT-3 has billions of parameters. GPT-4, we don't know. It's not announced. And training is a big challenge. Neural networks are so large. The data they're trained on is also extremely large. And there's one fundamental challenge in training neural networks. From my perspective, the first problem is non-convexity. Many machine learning models like least squares, logistic regression, these are based on convex optimization. This is actually important because whenever you define a loss function, there's typically a unique minimizer. The model is determined by that function. In the neural network case, it's not the case anymore because it is non-convex. You run some algorithm. It does have some parameters in it, like initialization, step sizes, optimizers. And it will find you something. And this becomes a very, very black box, which is hard to understand and also hard to train. From the theory perspective, even training a two-layer neural network is NP hard, unless P is equal to NP. So there are lots of open questions around this. How do we make training neural networks more efficient? How do we deal with high-dimensional data, high-dimensional models? And also underlying core problems are, how do we develop a foundational theory? And how do we interpret these models? So what I will try to show you today is, somewhat surprisingly, randomized embeddings, they play a very essential role in all three. Training them better, faster, more efficient. Also developing some foundational theory. It will be based on randomized embeddings, and also interpreting these models. What do they really do? This will also be in the language of randomized embeddings and sketching. The math tools we use in sketching, surprisingly, they pop up. They are things we encounter in neural networks. So here is the high-level overview. So first, I will introduce you a convex optimization model. These are reformulations of neural network problems, which are actually non-convex, but turns out that there's an embedding which takes them and maps to a convex space. And it will be a high-dimensional convex program. So we are trading off some kind of hardness, which is non-convexity, with some other kind of hardness, convexity, but high dimensionality. And this will be dealt with randomized embeddings. And there will be some global optimality and approximation guarantees based on randomized sampling. And there are interesting connections to zonotopes and Clifford algebra. OK, so I'll introduce you what randomized embeddings are. This is a mathematical construction. So basically, you have k points living in n dimensions. And there's a function f, which is mapping these n-dimensional points to m dimensions. And m is much less than n. What we want from this embedding is that the distances are preserved after the embedding. Approximately, we should have similar distances. And the classical embedding that we know in this field is the Johnson-Lindenstrass embedding. It's very simple. It is a linear map. So what you do is you generate a matrix S, which is m by n. It's a wide matrix. It reduces dimensions n to m. And what it does is, actually, with high probability, you see that the distances here are preserved approximately. if you have order log k dimensions in this embedding. And k is the number of points. Surprisingly, this number, which is the critical dimension you can embed to, doesn't even depend on the original ambient dimension n. It only depends on how many points you have. And this is actually a surprising result. It did have lots of implications in abstract math, functional analysis, yes, but also in the practice of algorithms. We use these type of constructions in algorithms, and this is actually what led to the work in sketching. It is possible to generalize this to any norm. You can embed from a p norm to a q norm, which means you look at the q norm of s times a vector z, and then you want to preserve p norms. Right? P and q can be basically anything. And here, the set of vectors, it doesn't have to be a discrete set, finite set. It can actually be a continuous, non-discrete set. It can be a subspace, for instance. Here's one example, a subspace embedding, which is actually very common in the theory of sketching. So we choose p and q equal to 2. We use Euclidean norms. And we take the set V, the range of a matrix. And this matrix will be n by d. And assume for now that n is much larger than d. And this will basically correspond to a regression problem. We have lots of samples. And the dimension d is smaller than the number of samples. So we generate a random S. There are many ways to generate this S. You can make it IID plus 1 minus 1, or IID Gaussian. And there are much faster ways, better ways of doing this. There are sampling-based matrices S, all other kinds. And it turns out that a random S will give you this result. Any vector z in the range of this matrix A will have its L2 norm approximately preserved when you choose the embedding dimension as low as, well, greater than rank of A times epsilon to minus 2. And here, rank of A is actually a small number because n by d, that matrix is a tall matrix, typically in regression problems, right? Rank is at most d, possibly smaller. And we are reducing from dimension n to the rank of A, which is at most d. So let me show you how this result is used in sketching. So let's say we have this least squares regression problem, which is basically about taking a vector y and then projecting it onto the range of A. And you might have guessed, if you preserve the range space information, right, you will actually preserve optimality approximately in this problem. If you have n rows and d columns, and n is greater or equal to d, solving this problem in the original space without any randomization is sometimes challenging if n and d are large. With direct methods, you need complexity nd squared. And if you have iterative methods like conjugate gradient, they will give you an approximation in order nd times some condition number dependent quantity. And with sketching, actually, this can be made much faster. So what is the process? Let's say we call the objective f of ax. It's a function of a times x. And then we call the optimal value opt. This is the original problem. And then A is a tall matrix, n by d, containing measurements. So you multiply this matrix on the left by S, which is this sketch, this random matrix. And then you get this tiny S times A matrix, which is m by d, right? And then the idea is very simple. You solve the approximation, which has S times A and S times Y, right? And since we know this S does not perturb distances in the range of A too much, we expect actually x hat, the minimizer of this, to be an approximation to this problem. So that's basically the idea. You can make S composed of IID Gaussian entries, but there are actually much better ways. You can form this product S times A faster based on constructions like the Fourier transform. This is inspired by work in compressed sensing. You take a Fourier transform and randomly sample the rows. That's one way. It will take order nd time, ignoring logarithmic terms, which is actually good. It is actually as fast as reading data in A. It cannot actually be faster than this. And if the matrix A is sparse, which is actually usually the case in machine learning, there are other constructions based on sparse matrices, and you can bring the cost down of forming S times A to order n and z of A, where n and z is the number of non-zeros in A. And this is pretty good. Actually, the fastest algorithms we know to approximate the solution to a constant factor and a 1 plus epsilon factor is based on these sparse embeddings. So here's one result for approximation of the cost. The earliest such result is due to Sarlos from 2006. And then over the years, this result was improved. And I worked personally in this area quite a lot. This is actually from our latest paper. So if you choose the embedding dimension as 1 plus rank times 1 plus 1 over epsilon, which is slightly larger than the rank, and the dependence on the rank of A is 1 over epsilon, then you will have a 1 plus epsilon relatively optimal solution. And it turns out that this is the best bound you can get. This cannot be improved. There's also a matching lower bound. This will happen with high probability. So this is the case. These are exact numbers with the Gaussian sketch, IID Gaussian sketch. For others, there are other formulas like this. There are other expressions, and then there are constant factors. The critical quantity is actually the rank of A divided by epsilon, controlling the error. And here's one practical application of this. Let's say you have a real data set. This is the airline data set, which contains flight, arrival, time of flight, destination, these kind of information. It's a real data set. 120 million rows and 28 columns. Okay, so it is data for 120 million flights. If you choose the embedding dimension to 500, you solve a really, really tiny problem, which is 500 by 28. And then you will get, according to these results, 1.06 approximation. And because there's 1 over epsilon dependence, if you add one more 0 here to the embedding dimension, you will have another 0 here. And it turns out that this is the optimal scaling. This cannot be improved. Question?
I think here you seem to be describing an experiment. Experimentally,
yes.
Does the approximation really match the 1 plus 1 over epsilon, or is it better?
Yeah, the question is, in practice, does this match exactly? Yes, actually, it does match exactly, because there is a result which shows that the approximation ratio is really concentrated around this value. So you have an upper bound and lower bound, and the concentration is exponential. This is the case with Gaussian sketch, though.
And some data sets don't turn out to be magical easily.
Oh, okay, very good question. Does this depend on the data set? Actually, the result is says no. It doesn't depend on the particular data set, because whenever you have a Gaussian random matrix, you multiply your data with it, it actually makes everything Gaussian. So it doesn't really depend on the particular data set. There's some sort of universality. Does that make sense? This is not proved for other sketches like sparse and Fourier Bayes, but for Gaussian, we know this is the case. It is actually universal. Very good question. Thank you. OK, so I will introduce you another kind of a sketch. This is what I call quantized embeddings. OK, this is actually a much more aggressive form of sketching. Let's say you have a set of points, and they are taken on the surface of the unit sphere for some reason that will be clear. And then we have a random matrix, m by n, reducing dimension, exactly same as before. But we take the sign of s times z for a vector z. So our embedding is actually to the Hamming cube. We actually get a +1, -1 bit string. OK, so this is much more aggressive. You reduce dimensions and then map it to +1, -1s. So I call these quantized embeddings because you quantize them. This is known as other things. For instance, locality-sensitive hashing is another way, another name for this. So what really happens is the following. In the space of z's, here it's z1, z2, we have these planes. S1 transpose z equals 0, the with normal S1, and then S2 transpose z equals 0. Depending on actually which region you fall into, right, in terms of z, you get a different pattern, right? It will be 1, 1 if you have positive inner products. If 1 is negative, you will have -1, right? So it divides the space into regions. And inside each region, there is a bit pattern, right? The vector is mapped to. So these are called hyperplane arrangements, which is basically a set of planes and the regions, the sets created in between them, right? We have chambers. And I call these are generated by the rows of S. The normals of these planes are the rows of S. And it turns out that there is a similar notion as in JL embedding to preserve distances. In this case, it's actually the Hamming distance is preserved relative to this inverse cosine distance, which is the geodesic distance on the sphere. And this holds with high probability if you have the sketch dimension set to logarithmic in the number of points. So in sketching and randomized algorithms, this is known as locality-sensitive hashing. It's exactly the same construction, right? You have a long vector, you map it to a bit string, and then the bit string is actually sensitive to similarity in the original space, right? And this has lots of uses. Another use is in compressed sensing, right? So you have a big high-dimensional signal, and it's mapped to just compressed data. From that, you might be able to reconstruct. And more recently, we actually applied these in compressing deep neural networks like language models. For instance, the llama model. It turns out that these are also quite useful in compressing language models like ChatGPT. And there are lots of other problems where randomized embeddings are useful. You can have a streaming setting. For instance, in the least squares problem, the data might be getting updated because maybe you're reading it from a big disk, or it's a temporal problem. You get new measurements at every time step, right? If the data is updated by some delta t, the sketch can be updated by just updating s times delta t. And if you're using a sparse sketch, and if the updates delta are also sparse, this becomes very efficient, and you always maintain approximate optimality. Well, you might be wondering what happens if the problem you have is not a tall least squares, but a wide least squares, some high-dimensional problem. It turns out that all of those are actually very similar to the one I showed, because in convex optimization, there's this notion of convex duality, which takes a problem and turns into a transposed form. You will have a least squares problem with the matrix A transpose, right? So if the matrix A is wide, you can take the dual, and then multiplying by S transpose on the left does exactly the same. So all of these things actually extend to the case where you have wide data matrices by taking transposes. There are also lots of applications in low-rank approximations, like speeding up singular value decomposition or tensor decompositions. Instead of solving the least squares problem in one shot, you can also construct a preconditioner based on these sketched matrices. This is also something explored in the literature. Previously, I worked on generic convex optimization problems like logistic regression, support vector machine, semi-definite programs, which all look like this with some large, tall matrix A. It turns out that actually you can apply sketching to the Hessian matrix. And then the Hessian matrix will be smaller, and you can run an approximate Newton method based on these sketched Newton steps. And finally, I know there's lots of work on constrained and regularized problems. The least squares problem can be regularized or constrained. And in those, actually, you get better results, because when you have constraints, the distances you want to preserve, they are in a smaller set. They are in a constrained region. And because of that, the embedding dimension actually can be chosen lower. In this case, it will be related to the width of the constraint set, which is called Gaussian width. So speaking of regularized problems, the most important constrained or regularized version of least squares that comes to my mind is this problem, L1 regularized least squares, right? This is called lasso. This has lots of applications in statistics and machine learning. What it does is it will induce sparsity in the solution X, right? And very useful if you have lots of columns of A and only few of those are actually relevant, predictive in forecasting, in predicting Y, right? So L1 norm is actually studied a lot, and it's very important model. And there's an extension of this model, group L1 regularization. So in this case, the vector X is divided into blocks, which we call G1, G2, etc., right? And then the regularization is not the sum of absolute values. It is the sum of L2 norms of these blocks, right? And what this does is it makes the solution what's called group sparse, meaning most of the blocks Xi at the optimum will be 0, right? So it's a generalization of lasso. This will reduce to lasso if you have a group size of 1. Right? This is the generalization of absolute value, basically. And this is also used quite a lot in statistics, for instance. You might have predictors which actually come in groups, and then you would like to identify the relevant groups, right? A group actually moves together, 0 or non-zero, right? This model is also well known. So this model will be actually very important in neural networks, and I think this was a surprise for us. So now I'll tell you about neural networks and this convex reformulations, which is actually an embedding that goes in the other direction of JL embeddings. So JL embeddings map high-dimensional data points to low dimension. And it actually turns out that if you have a non-convex problem, sometimes there's a way to embed them to high dimensions so that the problem will be convex. And I know some other instances of this in optimization, like in semi-definite programs. This is another one such case, I would say. So let's look at the simplest case of a neural network problem. This is the practically relevant simplest case of a neural network. So we have minimize some loss. This L is some convex loss. It can be squared loss. It can be cross entropy loss. And then X is our data matrix, N by D, containing samples. And we have two layers to be trained, W1 and W2. This optimization is over them, OK? And then Y is a vector of labels. And we have this standard regularization, sum of the squares of every trainable parameter, right? This is called the weight decay in neural networks. And this function phi is the activation function. You need this nonlinearity to make sure your neural network is actually not reducing to a simple linear model. And we pick that nonlinearity to be the ReLU activation, rectified linear unit, which is 0, and then x after x equals 0. And this was actually quite essential in the development of deep neural networks. When people switched from other activations, which are smooth, to ReLUs, they immediately get better results. And I will show you that there's actually something very special about these kind of activations. OK, so this is from our recent results, first published in 2020. It turns out that there's an embedding which will take this non-convex problem, map it to a higher dimensional problem, and the higher dimensional problem will be convex. So it will look minimizing the same loss over some variable matrix Z. This Z is D by P. OK, so P is some new dimension I'll introduce. And then there's some regularization R of Z. OK, this regularization is actually very different than the original one. OK, and it turns out that these two are identical in the following sense. Their objective values are the same, the non-convex one and then the convex one. And you can find an optimal solution, an optimal neural network with respect to the first one, using the optimal solution or an optimal solution to the convex problem. OK, so this is actually an embedding result. And why is this possible? It's possible because the dimension P is higher. In the low-dimensional space, you have something very complicated, a non-convex function, but there is a mapping to high dimensions, which will actually entangle all that non-convexity. And I'll show you what P is. And this is very interesting things like sketching will enter into the picture. OK, so let's see a specific case. We will choose squared loss so that it will be like least squares and in fact, later lasso. The problem is minimizing over two layer weights, right? The squared loss. And here I'm writing this over the neurons. I have M neurons in the non-convex neural network model. The convex model is the following. So this is actually just group lasso. It is actually exactly group lasso, which I introduced earlier. We have some dix ui minus vi minus y. The variables here are ui's and vi's. OK, di's are diagonal and fixed matrices. I will show you exactly what they are. These are fixed. These are not optimized. They are kind of mimicking what ReLU does. It will be a diagonal matrix with zeros or ones on the diagonal. And the theorem says that if you solve this problem, you can construct a neural network using this formula, which is just some scalar normalization of the solutions ui and vi. Basically, they are the hidden neurons, optimal hidden neurons. OK, so this problem is just group lasso. Basically, neural networks are, if you're using ReLU activation, these are just group lasso models using fixed features. And these features are di times x matrices. OK, so next, I'll show you what these are. Let's look at a very simple case. I will have 3 samples in dimension 2. because I can just plot them easily, I have 2, 2, 3, 3, 1, 0 here plotted on the plane, right? We will look at linear classifiers, in this case, this one, and we will look at the separation pattern. So in this case, all three are on this side of the plane. And because of that, the matrix D1 is diagonal with all ones, right? And this is kind of mimicking what a ReLU neuron is doing to your data set. It will basically pass some samples and then pass some others. But this happens in a structured way. There's this linear classifier, right, which is separating this one out. Because of that, you will have a 0 here. And the matrix D1 times X will be the entire training matrix. D2 times X will be training matrix with the third row zeroed out, right, which is actually what a single ReLU neuron does. And then if you look at other options, actually not too many options are available here. You can have this one too, 0, 0, 1, right? So basically, in this case, the neural network problem can be written as a simple convex optimization model. We have these DIX matrices, which are here, right? We have optimization variables, U1, V1, U2, V2, etc., right? These are constraints describing which side of the plane the samples are relative to U1, V1, which are just linear constraints. The interesting thing here is the regularization. We have sum of L2 norms, right? And this is a regularization you have in group lasso, right? So operationally, what this does is, at the solution, you will have very few non-zero blocks, UI, VI, right? So basically, this is doing the following. You have linear models associated to subsets of data, right? For instance, this model has weights U2 minus V2. It is linear, but it only acts on the first two samples. Likewise, this is actually acting only on the third sample, right? And with this regularization, you're trying to find the sparsest combination of these locally linear models, right? So this is actually identical to the ReLU neural network, which many people use in deep learning. OK, so what is the complexity? So you might be wondering if this is violating any kind of complexity theoretic lower bound. So it's actually interesting. If you have this model, f of x, sum of m neurons times second layer weights, how can we optimize this? Brute force, right? So you have m neurons, right? For each data sample, it will be on or off. You have n data samples. If you do a combinatorial search over n comma m, right, it will be exponential in n times m, right? M neurons and then n samples. You need to actually flip on or off all these neurons. And this is actually what the previous results were. These are combinatorial, and complexity is exponential in m and d times m, because they search over every ReLU pattern. But it turns out that this is not necessary. If you solve the convex problem, the dimensions it will be embedded to is this, n over r to power r, where r is the rank of x. OK, so it's only exponential in the rank of the data. And this is a big improvement relative to existing work. So there are two cases. If n is the number of samples and d is the dimension, if you have a fixed rank matrix, this will be polynomial in everything, n and m. And it will be a polynomial time algorithm. Given that you can solve convex programs with polynomially number of variables, it is polynomial time. Well, at least randomized polynomial time. The second case is when the rank is actually full, right? It's growing with d. In that case, it is exponential in d. And it turns out that this cannot be improved. Even if you're training a single neuron, we don't know any polynomial time algorithm. In fact, we know that these problems are NP hard. So it's actually not possible to improve this if the rank is full. OK, why is this interesting, right, if it's exponential time? And also, why do we have this number, n over r to r, right? Why do we have that? So it turns out that the number of variables in the convex program is the number of chambers you get in a hyperplane arrangement. So if you look at x times w sign, right, which is actually our quantized embedding, it is basically creating these arrangements, right? You have n planes, whose normals are your data samples, rows of x. And if you look at these regions in between these arrangements, the number of those chambers is bounded by n over r to power r. It can be actually smaller, but this is an upper bound. And R is the rank of X. So the interesting thing is, in convolutional neural networks, this rank is constant. Okay, and it will become fully polynomial, meaning polynomial with respect to all dimensions. And you can solve this in randomized polynomial time. So for instance, a typical convolutional neural network will have layer sizes of 3 by 3 times 124, indicating 3 by 3 is the spatial size of the convolutional filter. In this case, it will be polynomial time. So what happens if it's not? It can be fully connected, right? Then we have lots of variables in the convex program. And then the question is, how do we solve these problems faster? But luckily, we know many ways. If you have a very high-dimensional problem, just like a very tall least squares problem, we can actually apply sketching and randomized sampling to it, right? And there's actually a very natural form of applying this here, because the DIs here are diagonal blocks, which is generated by this quantized embedding, right? So the idea is we will randomly sample these variables, we optimize over them, and set the rest to 0. Okay, so we will optimize over a random set of coordinates, basically. But the goal here is to sample proportionally to some importance measure, because I want the important variables to be optimized over, right? Maybe unimportant or less important ones we can drop, right? That's the idea. So how do we come up with something like this? It's actually very simple. So look at how these DIs are generated. So it's a diagonal pattern with this x times ui non-negative as its indicator, right? It's ones and zeros. And this is exactly these quantized embeddings. If I generate lots of ui's, by say 1,000 ui's from any distribution, it can be IID Gaussian, and I look at x ui greater or equals 0 coordinate-wise, it is a pattern, right? And basically, I'm just applying a locality-sensitive hash, right? So the data points are mapped to the 0, 1 patterns, right? Each one is assigned to a subset, right? And then we minimize this convex program, right? Basically, it is applying random hashing, this quantized random embedding, and then we are training these ui minus vi's, right? This will be the idea. Any questions up to now? Okay, so how can we analyze something like this, right? Basically, we have randomly sampled variable blocks, right? These DIs are randomly sampled. It turns out that this is related to an interesting topic in convex geometry called zonotopes. So zonotopes are basically convex polytopes. How they are defined is you look at the convex hull of some xi ui, where ui is either 0 or 1. Okay. Another way to define this is you take the hypercube, right, of sides 0 to 1, and then multiply it by x transpose. And recall x transpose is a tall matrix. X is a tall matrix, x transpose is a wide matrix. So it's a linear projection of the unit hypercube, right? So some vertices of the hypercube will basically disappear after this projection. Some will survive projection. Here's an example. If you have x1 and x2 as 2 rows of your matrix, the zonotope generated by that is the convex hull of 0, x1, x2, and x1 plus x2, according to this, right? And it is this set, this diamond-shaped set with 4 vertices, right? So if you generate a random vector h and maximize this linear function over the zonotope, you're looking for the support functions and support points, right? And you can see that this will happen at vertices, right? Linear functions are maximized over vertices of a polytope, right? If you pick this h, actually, you will find this vertex. If you pick h in this direction, you will find either this one or that one, right? This is actually what's happening if you're running this quantized embedding or this random sampling process. And you will find a particular vertex if the vector h happens to be in this cone, right? And each vertex has an associated cone, right? These cones are actually describing how important each vertex is. You can actually have a vertex which is almost not a vertex, right? A very non-sharp edge, right? In that case, the cone will be actually very narrow. But that means actually the variable is not important. It's almost a non-vertex. And if you look at the maximizers of this linear function, this is actually quite simple and surprising. If you maximize this over ui for a given h, you will see that the result is sum of xi transpose h plus, because you can choose ui optimally 1 xi transpose h greater than 0. Just pick it 1 if it's on one side of the plane, right, with normal h, and 0 otherwise. It will maximize this. And this is actually showing that the maximizer is exactly this quantized embedding, right? Argmax of the linear function is 1 xh greater or equal 0. And this shows that the hyperplane arrangements have a one-to-one mapping to the vertices of the zonotope. Each chamber here, right, in this quantized embedding is actually mapping to a vertex. And based on this, actually, we can randomly sample the vertices of the zonotope, which is same as sampling chambers of the zonotope. And these kind of ideas were actually explored in computational geometry before. So it turns out that the hardness in the sampling problem is controlled by the angles of the cones, right? Each vertex will have a cone, right, which will show you when you will end up in that vertex if you sample a random h vector. And we can define this sort of importance measure, theta I, which is proportional to the probability that you will end up in that vertex if you sample a normal vector h, right? And this is proportional to the solid angle, how much area is covered relative to the unit sphere surface area. And we look at the minimum of these angles, because minimum one will dictate how hard the sampling is. So here is the main result. So sample these DI matrices by generating random Gaussian HI, okay? And this is same as apply locality sensitive hashing to your data to get these DIs, right? Each is telling you which bucket the data fell in. And the theorem says that for any integer k, we can obtain, by solving this reduced subsample convex program, we can obtain a 1 plus epsilon approximation, where epsilon is k plus 1 singular value of x divided by lambda, which is the amount of regularization in the neural network. And if we do that, we will have some number of samples. Solving the convex program will require n over k to power k complexity times inverse of theta, right? And here theta is the minimum solid angle of the zonotope. So basically, we reduce the complexity from exponential in some dimension to exponential in k, right? Where k is the index of the effective singular value, basically reducing exponential in d to exponential in some effective dimension, right? If you have some data with decaying singular values, k will be the value of the index, right, which makes a good trade-off. And it turns out that actually, if you really solve this convex problem, look at how the neural network performs and compare it with non-convex optimization, right? For instance, stochastic gradient descent. Here, that's what we do. In a simple benchmark, here it's CFAR10 image classification data set. It turns out that as you sample more, this is the number of variables we sample. As you sample more, the accuracy increases. This is test accuracy, and it actually exceeds the accuracy you get with non-convex optimization. So non-convex optimization is actually very similar to what's happening here. It is randomly initialized, right? But it is updated through non-convex gradient descent. Here, we have some random initialization for getting these patterns, right? Which is some hashing of the data. And we solve the convex program in just one shot. We use a convex optimization solver. And then you get actually better accuracy, which is actually interesting. So to me, the most surprising thing is the non-convex gradient descent doesn't even optimize these patterns. If you randomly initialize these patterns and then solve the problem, it works even better. And this was actually very surprising to me. And we came up with this optimization toolbox for neural networks. And we have a performance profile. This is done over 400 data sets in the UC Irvine collection. We declare a problem solved if you get near 10 to minus 3 within the global optimum. And we plot the proportion of problems solved within this 400 data sets. And we compare with Adam and SGD. And those, we actually take 10 random initializations and 10 different step sizes, and we take the best of them. For our method, we only solve the convex program just once. And the step size is automatically selected by the optimizer using line search. It turns out that actually you can get all these problems solved to global optimality or near global optimality in under 15 seconds, whereas the other optimizers do not even solve all problems, and it will take a very, very long time. And from the optimization theory side, we know why this happens, because non-convex optimizers are solving a non-convex, non-differentiable problem due to the ReLU activation. And the convergence rate, at best, is to a stationary point, and it will be 1 over root number of iterations. In the convex optimization world, if you have a lasso-like problem, actually non-differentiability of that is not really important, because we have proximal algorithms, and the convergence rate will be 1 over number of iterations squared. There's a question.
So for this plot, are you fixing the like the model, like the neural network two-layer model?
Right. This is for two-layer neural networks, the model I showed.
And then does this plot look the same if you sort of vary the model?
Oh, OK, very good question. The question is, does this change if we vary the model for all two-layer neural networks, which are fully connected or convolutional? It will be like this. But if it is deeper, it will be different, which I'll probably come back to. If it's deeper, then it's a different issue. And I'll show you what happens. Good question. OK. And I promised you to show that actually interpreting these neural networks become easier with randomized embeddings. How does this happen? So let's say you have some signal, right? It's just an array. And we are trying to predict the next value using a neural network, right? So how this works is you have some data frame from here to here, and you're trying to predict the next value, right? And you fill your data matrix by sliding this time window, right? And then you run your neural network. You train it, right? It's very, very common. So if you look at this convex program, and the DIs are randomly sampled through this quantized embedding or locality-sensitive hashing, right? What's really happening is you have these little signals. These are the time windows, my samples, right? You have a hashing function, which will hash it to a different bucket, right? And over each bucket, you have this linear model. And this one will actually pick the most concise explanation of why, right? And of course, this makes a lot of sense, because if you go back to the signal, over here, I have a very sharp change, right? I need a different kind of model than the one which is working over here, where there are no jumps, right? It breaks down your signal into multiple blocks using hashing. And then over each block, it is learning a linear model. Of course, this works much better. But I can interpret it as just hashing, right? So I claim that this is more interpretable than just running this black box neural network model, because at least we know what the model is exactly doing. OK, so finally, I will show you a framework to unify all of the things I said. And I think this is providing a new avenue for randomized algorithms and sketching. So this is called Clifford algebra. So here is the interesting thing. I showed you that group lasso is what is neural networks with ReLU activation, right? What happens if your data is one-dimensional, which is still a meaningful problem? You have one-dimensional points, right, and labels. And the group lasso problem reduces to lasso because group size is 1. And we thought this is interesting. What happens then, right? And it turns out that all of the constraints, they disappear in one dimension because they're already satisfied. And it turns out that you get this lasso problem in the convex neural network, which looks like this. It's just this lasso that I showed you with some matrix K, right? No constraints. We are optimizing over alpha and b. This is a bias term. And the matrix K is defined as xi minus xj plus for each ij. OK, and what is this doing? What is this doing is basically you have some samples here, x1, x2, x3, etc., right? It is actually fitting you a piecewise linear function, right, with breakpoints at data points. But not every data point. It is actually a subset of the training set, because lasso will have a sparse solution, right? And in this case, the zonotope will have vertices at these data points only, right? And when you're sampling, you're basically sampling these breakpoints. OK, makes sense? And this was interesting. So it is just a piecewise linear model, right, in one dimension. And the kings are some subset of the data. So Then we realized that this formula xi minus xj plus for the value, this looks like a kernel matrix, if you know about kernels in machine learning, right? It's like a kernel matrix. But it is different because you're solving lasso. This is not a kernel method. We realize that this is actually the volume of the interval from xi to xj. But it is the signed volume. And if you take ReLU, it is the positive part of the signed value. Basically, it's like a signed distance, right? So xi minus xj plus is going to be 0 if xj is larger than xi, which is on the other side of xi, right? If it's on the opposite side, it is actually measuring the distance. In this case, it is just the volume, right? And it turns out that there's a very natural generalization of this to high dimensions. For instance, in 2 dimensions, here is the convex program, right? And Kij will be the volume of the triangle between the origin, xi and xj. And this is actually a signed area. If the order of 0, xi, xj is counterclockwise, it's positive. If it is clockwise, it is negative. And plus, we'll make it 0 if it is clockwise. And then there's this 2 over xj L2 norm. And it turns out that this is actually almost a neural network problem, because this is the natural generalization. And it turns out that in any dimension, there is a formula. This will give you the neural network model approximately in the following sense. So Kij is going to be the volume of the parallelogram spanned by these vectors, which are just data samples. Okay, and these indices, they actually range over every size D subset. The J is actually a multi-index, and when you form the K matrix, it is actually a very wide n by n choose D matrix. And there's some normalization here involving the cross product of these vectors. And it turns out that if you have this inequality, which is actually just saying X is an L2 to L1 subspace embedding, right? One of the first inequalities I showed you. If you have the matrix satisfying a subspace embedding property from L2 to L1, this is not L2 to L2, with parameter epsilon, then this will give you an epsilon optimal neural network. So it's actually very, very close if you have a nicely distributed matrix. And we know that this condition will hold if you have a random matrix, say IID Gaussian, and then the number of samples exceeds D times some factor of the epsilon. Here, I think the best is epsilon to -4. So for random data, it is actually the case that neural networks are approximately lasso models if we have the matrix as a subspace embedding. So where does Clifford algebra go into the picture? So basically, Clifford algebra is a very nice mathematical tool which generalizes linear algebra, complex numbers, quaternions, cross products. If you actually know about this, you don't need complex numbers. Here in this field, you have multivectors, which is a sum of scalars, vectors, bivectors, trivectors. You have these higher grade objects. You form a wedge product of 2 vectors. It is actually representing the oriented area. You can think of that as a parallelogram. In this case, it is this area spanned by A and B. It is signed. You can have B wedge product A, which will be minus A wedge product B. And there's a way to define a product, which is dot product plus wedge product. And it turns out that there will be a multiplicative inverse. This operation is invertible. And there's a notion of dual, which is giving you complementary subspaces. If this was 3-dimensional, the dual will be actually the cross product. But it turns out that this exists in any dimension. You can define these duals in arbitrary dimensions. So it turns out that this convex program, you can write in terms of the Clifford algebra. So Kij matrix, which is previously as stated via volumes, right? It turns out that it is actually the ratio of 2 things. At the top, you have the wedge product of your input sample with a subset of training samples. And then you have normalization by L2 norm. And through some operations in geometric algebra, this reduces to the distance of xi, the ith data point, to the affine hull of other data points, d of them. So it turns out that there's this interesting formula This kernel matrix is basically measuring distances to affine hull of subsets of data. And you have every possible size D subset in the training data, which is representing something like a concept. And xi is projected to it, and you measure the distance. And it turns out that there's a formula for the optimal neurons. The neurons can only be scalar multiples of the duals of this wedge product, which are perpendicular. It's the orthogonal complement of this object. So basically, by running this quantized embedding, we are getting subsets, right? This is the locality-sensitive hashing, right? We are getting a subsampling of these indices. And then we are basically subsampling this Clifford algebra. We are solving the convex program, right? This is actually how the results work. And the problem is actually this is very high dimensional in the case of typical fully connected neural networks, right? There is also an alternative scheme, which is hinted by this. If you sketch the data by mapping the data x to x times s, apply a JL embedding on the right, it is also preserved with an epsilon, since all of these are in terms of distances of affine hulls to the training data points. So if you sketch it on the right, you will also get preservation in terms of the optimal value. OK, let me conclude here. So basically, neural networks are high-dimensional convex models. I think this is one of the important results I talked about, right? And we had this approximation mechanism, which is applying random sampling, and you solve the reduced convex problem, and it will give you a neural network, which is approximately optimal. And there are lots of open problems. I think one open problem is designing better sampling strategies and better hashing, better sketching for the convex program, which will give you ways of making the neural network training or maybe inference also faster. And I think exploring sketching and sampling in the field of Clifford algebra is a new way. I haven't seen any results on that. I think this is a very promising avenue. Thank you very much for your attention.
Thanks, man, for a great talk. Any questions?
Yeah, thanks for the. Okay, well, I'll shout louder. Thanks for the great talk. I'm wondering, like, as a high-level question, do you think there are any lessons that? Do you think there are any lessons that people in the applied deep learning community can take away from your work? Because it's very hard to change their mind to like do something totally different. But do you think there's sort of like tidbits that they should take away in what they're doing right now?
Yeah, that's a very good question. So I think there are a couple things. One is improving the optimizers, right? By looking at the form of this convex program, actually, it's immediate that you need to use a different optimizer, like a proximal optimizer. And there's already some work by other groups using these proximal steps. That's one. And I think the second thing is about interpreting these models and simplifying them, even looking at the ones as big as ChatGPT, right? And then interpreting them through the lens of random hashing, and later actually simplifying, pruning, compressing these neural networks so that you get better efficiency. And maybe finally figuring out why these are generalizing better than other models. That's another thing you might be able to do with these convex parameterizations and random hashing.
Any other questions?
So you mentioned they generalize better. Have you looked at like the test error as well, or like it is like exactly like your training error in the plot?
Very good question. I can show you some plots. For instance, this is one simple experiment in C510 image classification. On the left, you see training objective value. These trials are for stochastic gradient descent, initialized at different points. So they go down almost to this dashed line. And this dashed line is actually the objective value we find by solving the convex program. We know that that's the optimum. And they almost reach there, although there's a gap. This cross is the time it takes for our convex solver to solve the problem. As you can see, it's a little bit after this point, but it gives you a better objective value. Then the question is, if you optimize a little bit better, maybe 10 to minus 2 order of that better, do you get better test accuracy? Interestingly, it is true. If you look at the test accuracy, this model, the convex model, by doing this tiny bit better, in training accuracy, it actually finds a much better decision region. And I think that's true because even if you perturb your neurons a little bit, the decision region actually becomes better, and it can be much, much smoother, right? And you actually get a bump, an increase in the test accuracy, which is interesting.
If I understand correctly, these are for two-layer neural nets, and you mentioned that for deeper nets, things change. Could you say more?
Yes, okay, that's an excellent question, right. So all of the theory I presented you was for two-layer neural networks. One natural question is, what happens if you have one more layer and one more layer and one more layer, right? So what happens is, so this is done in the latest NeurIPS paper. If you have a three-layer neural network, right, turns out that there is a convex program, but there will be even more variables in it because you will have these di times dj patterns. And right now what happens is you get these hyperplane arrangements, and inside each arrangement, you have another arrangement, which is actually subdividing the existing arrangements. Because of that, you have more variables. And this is true as you are adding more layers. You will have more and more variables, although you get a convex program. And there are ways we are still exploring in how to sample it better. But let me also mention, there's one more way. If you can train a two-layer neural network, you can actually come up with a deep neural network very easily by training layer by layer, right? You train one two-layer neural network, keep the layer you learn, and then keep it fixed, learn one more layer, and then learn one more layer. Actually, people came up with this idea in deep learning to make sure the GPU memory is enough for training, because the entire network might not fit, but a single layer can fit at a single time, right? And if you do this, actually, you get pretty good accuracy. By the addition of each layer, you see the test accuracy getting improved. So right now, the problem is actually solving these deep problems in one shot. That's why we are having some sampling issues. There are lots of variables. And then the other alternative is to train it layer-wise, which is working in practice.
And to the layer-wise training, I imagine your convexification techniques do apply.
That's right. That's right. For this layer-wise, each step is actually convex optimization, right? In fact, you produce a deep neural network entirely using convex optimization. Each layer does solve a group lasso problem.
Time for one last very quick question.
Thank you. So as far as I know, so when we define random variables over Clifford algebra, so we don't have too many concentration techniques that we can use. Do you think that could be challenging for the research direction you mentioned?
Oh, okay, very good question. So I think, yeah, you're raising a valid point, which is in Clifford algebra, we do not have enough mathematical tools like concentration. I think that's true. But for some problems like tensor sketching, right, there are mathematical techniques. And I think this Clifford algebra will be similar. So what's happening is basically, in this case, there are these wedge products, and they're generating high-dimensional objects. And there's too many of them because there's a combinatorial aspect, right? And then by applying randomized hashing, we reduce the combinatorial aspect to it, right? This is, I think, working OK. But if you want to sketch a wedge product, I don't know entirely how that can be done, but maybe you reduce dimensions like JL and then take small dimensional wedge products. So what I meant was that. But I mean, it's exciting because I think this is not known in the field too much. And tools are going to be interesting.
Okay, let's thank Mert one more time.